All right, welcome back to physics. We started in on a series of energy charts last time, and we're going to continue on with those. So I'm just going to go right back on into Cami. And so if you need to know how to get into Cami, go and look at the previous video. All right, so today what I want to do is begin to investigate what happens in a system where a person is bungee jumping. So in this case, we start out and the person is way up high, maybe on a bridge or on a building or a crane. And then they jump off, and at the very end, they're hanging upside down from their feet, and the bungee cord is stretched out, and hopefully they have not hit the ground. So let's take a look at this system the way we did these previous ones in a before and after situation. So I'm going to start out here and I'm going to say our red is our potential energy. So our jumper has potential energy. No kinetic because they're just standing up there. No elastic because the bungee cord has not stretched. The next thing, so I should put that up here in the starting one. Okay. All right. And then I'm going to get rid of that one. All right, let's go on. So the bungee cord's not stretched and the total energy in our system looks just like that. All right, now, once he's jumped, he or she has jumped and they're hanging upside down and the cord is stretched. Well, at this point, the jumper has only a little bit of potential energy because they're very close to the ground. The jumper is going to have there's a lot of elastic energy, but there's no kinetic, okay? And so the total energy in this system is the same, I'm going to put my red one up there, is the same as when we started. So notice the total energy, we started with all potential, and now a big chunk of that potential has been transformed into elastic energy. So wasn't there some kinetic in here somewhere, maybe in the middle? Well, let's take a look at it. We'll break our system down a little further. So now, if we have our jumper at the very top, position 1 up here, the jumper in gravitational potential energy, yeah, there's a lot, but there's no kinetic and there's no elastic. And so the total just looks like that. We know at the bottom, there's very little gravitational. There's probably maybe a little bit of kinetic, and then a whole lot, okay, of that. So when we look at the total, we've got the elastic, we've got a little bit of kinetic, and a little bit of potential, the green and the okay? And so the total again equals the total. Well, what about the middle? Well, in the middle, if I say this middle part, there is less potential energy, okay, because the jumper and even less potential energy here. And on the kinetic side, well, now there's quite a bit of kinetic energy, okay? And there's still some kinetic energy here, but our elastic energy, none here, but there's getting to be some elastic energy here and growing there. So the important thing when we get to here is that if we take the total of all of these, okay, the total of all of these is all the same. And the reason is that the amount of energy cannot change. Okay, it can be transformed, transferred, but not changed. So these 4 questions, what those ask or talk about is what we just talked about, how that energy is moving around in there. So if you would like to, I'll show you that. You can stop the video, take a screenshot of that, and then you'll be able to move that over into your other work. All right. So let's go ahead and we'll move down just a little bit further. I'm going to go into Cami here because we're going to skip pages 8 and 9 and go into page 10. So in page 10, what we want to do is begin to fill out our form here for our pattern. So in this case, gravitational potential energy, our equation is mgh, okay? Mass times gravitation times, and g is always equal to 10. All right, so if we wanted to do a calculation, we could say, well, let's see, if h is 1, g is 10, and the mass, okay, right there is 8, then we know that this is 80. And if it was 2 times 10 is 20, 20 times 8, that would be 160. All right, if we go over to the next one, kinetic, our equation for kinetic, you can get this from our word wall, is 1/2 the mass times the velocity squared. So we have to square the velocity. I'm going to suggest you start at this right side. So velocity is 1 times 1 is 1 times the mass of 8 is 8, and take half of that, and the energy is 4. Let's do another one. Velocity is 2, so 2 times 2 is 4. 4 times 8 is 32, and half of that is 16. All right, so you can fill out the rest of those. Our equation for elastic is 1/2, and then that is K. K is our spring constant, times the distance that we stretch the spring squared. That's the equation for that one. So it looks very much like our kinetic equation. So in this case, if the stretch is 1 meter, it would be 1 times 5. So 1 times 1 is 1, times 5 is 5, and half of that would be 2.5. All right, so now when we move to this next block, understand this block of numbers has nothing to do with this block of numbers. These are totally independent. So if you're looking over here going, well, height of 2 and gravity of 20, where is that? No, it's 160. I know that, okay? The way this sheet is designed is that these three are independent of this one, all right? So in order to get the total, we're gonna add these three up. So we're gonna take the gravitational potential energy plus the kinetic energy, okay? Kinetic energy plus, I got to make that, let's try that one more time here. Okay, so plus E kinetic, and then plus EE, all right, plus that one, the elastic. Okay, so over here, if our total energy is 50, and we've said at the highest height, the person is just starting out, they're standing on the very, 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 very top. They haven't moved yet. So there is no elastic energy, and there is 50 joules of potential energy, because 50 plus 0 plus 0 equals 50. Well, on the second one, the person is now moving. The total energy has to still be 50. It cannot change. So how much is their kinetic? Well, I don't need to know their velocity if I know these other numbers, because I know that gravitational potential energy plus kinetic plus elastic must be 50. Therefore, this one must be 30. And I can do the same thing here. I know this has to be 50 because the amount of energy cannot change. And so if that's 10 on kinetic, 30 on elastic, this one must be 10 joules, because 10 plus 10 plus 30 is 50. And I'm basing this all on conservation of energy, that this one has to be 50. And if this one plus kinetic plus elastic is the total, then these two must be 0, all right? I want you to go through, figure up some graphs from this, and then tell me the pattern, whether it's horizontal, linear, quadratic, or inverse, okay? And then answer these last few questions at the end. All right, so I will see you next time.